Okay. Good afternoon, everyone. Let's get started. So first of all, don't forget we got homework 0 due on this Friday. So if you haven't started, please start right now. Otherwise, you might be feel too stressed at the last day. And also, our office hours have already been open since today, because Monday is a holiday. And we have updated the office hour information in the course website. Also, we made an announcement on the cameras. So please do take advantage of the office hours and seek for help if you need it. Okay. So in the first week, we spent quite much time talking about the course policy, the schedule, expectation, and also how we kind of grade your course project, homework assignments, all kinds of stuff. It's kind of tedious and it's kind of like boring. But again, please bear with me. I just want everyone to be crystal clear about how this course is organized, and what's the possible challenge, what is the other things you need to pay attention to, right? So starting from today, we're gonna talk about the topics, right? Talk about the things about probabilistic learning. We'll start with some basics review. This is based upon the fact that you're familiar with basic linear algebra, basic calculus, and basic statistic concepts, but we're going to introduce something beyond that. It's not just repeat what you have seen in your like calculus 1 or calculus 2. Okay? But again, this review, because of the time limit, this cannot be, sorry, let me use another color, comprehensive or in-depth. We just want to give you some important introduction about those kind of key concepts, right? So we list the key steps of doing some kind of things like matrix and vector derivatives, as we will discuss in a minute. But if you want more thorough review or exploration, we'll give you the reference. You can take a look and spend 1 weekend to take a look at that. Okay. Okay, we're gonna start with the matrix vector derivatives. So before that, we're gonna introduce some like standard notations. Right? So it's always good to keep those notations in your paper writing or technical report to avoid confusing other people. So in the whole world of algebra, we usually need to deal with scalars or numbers, vectors, and matrices. Right? Sometimes you might need to deal with tensor, but in most cases, like we just manipulate up to like matrices. How do we differentiate those 2 or 3 types of symbols? Right? So usually that's by default, right? If we use some letters which are not bold, which are kind of italic, it usually means it's a scalar or number. Okay. If you use small case letters, but it's bold, then it usually represents vectors. So like this, both small a, both small b, it just means a vector, b vector, and so on. Okay. And when, how shall we represent the matrices? Please use big case letters and bold. In most of scientific literature, people use this like by default. However, there is some kind of places that people kind of like mess those up. That's really not a good idea. I've seen a bunch of papers doing that, but to be clean, to be clear, and to be to avoid any kinds of confusion, please keep this customs or keep this standard. Right? Use smaller, use non-bold letters to represent scalars. If you want to represent vectors, please use small case letters with bold. And if you want to represent matrices, please use bigger case letters, bold. Okay. So now let us talk about the general definition of derivative or gradient. So we're gonna start with the one we are all familiar with. Right? Suppose you got a function which is just the scalar function. You can view it as y, right? And the input is a scalar x. Right? So how do we define derivative or gradient? How? Right? If we open our calculus book, it tells that, okay, if we want to calculate the derivative or gradient of y of x at some particular place, right? You can write it as a limit, right? A limited fraction such that you calculate the ratio between two differences, right? The first difference is the function difference, function value difference. That is, if you perturb your input x by a small amount like delta, right? You look at how much changes in the function, right? Then you divide this function value change by the input change, right? So if we can show that if this perturbation delta goes to 0, meaning that the limit of this fraction exists when delta goes to 0, and then we said y is differentiable at x, right? And its derivative of the gradient is this limit, right? It's just I recite what textbook says, right? And there's another way, but it's totally equivalent to represent this, is trying to represent the function difference in another way, right? You just multiply the denominator to the left. Okay, do that, right? If we can write our function value after you perturb your input by some delta, but here we're going to use a derivative of x, it's called dx, right? So if a function value after you perturb x by dx can be written as the function value at the original position x plus a linear term. So a times the derivative of x dx and plus a Helder term. So what does Helder term mean? Right? Yeah. This is just our examples, right? But in general, we say like Helder terms. If I say, okay, it's Helder term of x, it just means if you divide this Helder term of x by x, if you take a limit of x goes to 0, then this fraction goes to 0. Okay? This basically means asymptotically, when x goes to infinitesimal, then this Helder term can be ignored, right? To be very, very small. Right? So if you can find the a such that you can write down your function value after you perturb x by dx is equal to a linear form, namely yx plus this a times dx, then plus a much smaller term, which is called Helder term. Then we call the derivative of y over derivative of x is simply a. Okay? This is a more general notation, like if you use a partial derivative, that is to talk about, okay, if your if your y has many input variables, right? Or a current notation is that dy equals to 8 times dx. Right? Does it make sense? I'm just reviewing what you have saying before, right? I'm just reviewing what I have learned during my undergrad school. Right? It makes sense, right? Okay. So now, let us try to generalize this definition to vectors and matrices. So suppose your function is still a scalar, meaning that the function output, a function value is still a number, right? But the input is a vector. So see, you got n-dimensional vector. That means your input actually consists of n elements, right? And then the derivative of x, you can view it as n-dimensional vector as well, right? That's basically the derivative of each element in x. So dx1, dx2 to dxn. Okay. And then if we can write down the function value after you perturb x by a small delta, which is dx. Right? If you can write down yx plus dx in this form, meaning yx plus some row vector a times dx, then plus some higher order term. Then we define partial y over partial x, which is vector, by a. That's how we define derivative for vector input. So here we should be aware of something, right? First, dx here is a vector, right? And you see that yx plus dx is still a scalar, right? Remember, y is a scalar. So we just mentioned yx is a scalar. So if you want this guy to be a scalar, it must be a row vector, right? That means this is essentially some row vector times some column vector, right? So this guy is dx, and this guy is a. Okay. And this higher order terms, they have some kind of like more general definition. It basically says, so because x here is a vector, right? You cannot directly divide something by a vector, right? So usually it becomes a norm of x, right? And higher order term means that, okay, oh, sorry. We're gonna assume this higher order term will be a vector as well. So higher order term, higher order with respect to x just means if you divide their norm, right? If you calculate different ratio of their norm, if the norm goes to 0, then this ratio goes to 0. Okay. So in this way, we can define the derivative of y, right, as a row vector multiply the derivative of x. Right? So any questions so far? Is anyone feel uncomfortable, unclear, or confusing? Okay, perfect. So now let us extend to a even more general case. Suppose your function has a vector output and has a vector input. So basically means that your y now is a vector of m output. Okay? And their input is still this n-dimensional input. And of course, the derivative of x will be this n-dimensional vector as well. Right? And then how do we define dy over dx or partial y or partial x? Right? They're roughly can view them as exchangeable. So if we can write that after you perturb your input vector x by dx, the vector function output y can be written as the vector function y at x plus a times dx plus somehow the terms. Then we will define partial y over partial x equals to a, or dy, the derivative of y equals to a times dx. Okay. So now, what's this? Is it scalar or is it a vector? Y is a matrix. Don't tell me that you look at this. So this is a matrix. You need to explain why this is a matrix. David. Yes, exactly, right? So just keep in mind, whenever we're talking about matrix vector operations, you need always think about the size. You have to match their size. And once you figure out the size, then most problems or most issues have already been addressed. Right? So because now we're dealing with a vector output, right? So this guy is m by 1 vector, right? And this guy m by 1 vector, right? So this dx is n by 1 vector. Okay? So of course, if you want to multiply a with dx and n with another n by 1 vector, it must be a m by n matrix. Okay? So it must be a m by n matrix. That's why it must be a matrix. So now, what does this A mean? Yes, exactly. Right? This is what the definition of Jacobian. Right? So each element like A, I, J, according to what we have seen in the textbook, is actually defined as a partial yi over partial xj. Right? Because each row, remember, it has m rows, but each row corresponds to one output, right? One element of y. Okay? And each column has n columns. Each column corresponds to a one element in X, right? So Aij, column I, row I, column J will correspond to partial Yi over partial Xj. And equivalently, we can write down the derivative of y dy is this Jacobian matrix A times the derivative of x dx. Any questions so far? Everyone's happy, right? Okay, so now from the definition of derivative, right? So the definition of derivative, if you write down the difference between your function value after you perturb your input, right? This is essentially can be viewed as some kind of Taylor expansion. Right? You remember, so it's definition of Taylor expansion, but we just do a very simple first order Taylor expansion. We can see that no matter it is scalar form or scalar to vector or vector to vector form, it also has the same kind of like definition. That is, if you can write down the derivative of the function value, can be written as a linear transformation of the derivative of the input. So then we define the gradient partial y over partial x as the derivative A. Okay? This is the most general case where big A, you can view like, okay, if it is just 1 by 1 matrix, which is scalar, it returns to the scalar case, right? If A is 1 by n, right? So that means your output Y is just a scalar. And then it is a scalar to vector case, right? If it is m by n, then that is the most general case, like you have m output, you have n input, so your gradient is m by n. Does it make sense? That's our definition. Later I will talk about another definition. So that means we can define our gradient or partial gradient in a more general sense as the derivative. Right? If you can write down dy equals a times dx, we call a as the derivative. Right? So I say, so this is consistent with the definition of Jacobian, right? And you will see that it's usually very, very convenient if you apply it to composite functions, because you can apply the chain rule from left to right, which is very, very natural for human beings. Right? There's only one thing you might feel uncomfortable is that if your output function is a scalar, then the gradient is a row vector, right? As we just mentioned, right? So if your y here is a scalar, so A here must be a row vector. You only multiply a row vector with a column vector dx, you end up with a scalar, right? So if you define our gradient as the derivative here, then you should be just to pay attention that for output scalar, for the scalar output, the gradient is a row vector, not a column vector, as you might commonly assume. But what's the benefit? Let us look at if we apply the chain rule to compute the gradient. So suppose I got function y is a function of x, right? M is m by 1, right? So it's a m dimension output, right? And x actually is the output of another function of z, which is namely x equals to gz. And x is n by 1, z is q by 1 input, right? So now if I want to compute partial y or partial z, according to our definition, we know that partial y or partial z should give you an m by q matrix, right? Because y has dimension m, z has dimension q, right? So it should be m by q, right? And how do we compute that? We can apply the chain rule, right? So we can first compute the partial y over partial x, which is actually the gradient of f, right? And then times partial x or partial z, which is gradient of g, right? If we insist on our definition, right? Partial y or partial x will be m by n, because y is m by 1, x is n by 1, right? So partial y or partial x will be m by n. And partial x or partial z will be n by q, right? Because x now as output of g is n by 1, right? And z, the input to g, is q by 1. So partial x or partial z, according to our definition, the Jacobian is of size n by q, right? So now we can simply multiply the two matrices together, we get our partial y or partial z, right? So you can see that if you define the gradient or partial gradient as a Jacobian, then we'll compute the gradient of the composite function. We can just apply the chain rule and multiply the Jacobians from left to right. Right? It's very natural. Does it make sense? It's very natural. you can assume like z equals to s w, right? And z w is another like P by 1 vector, we can continue multiplying the Jacobian. That won't be any problem, right? But what if define the gradient in another way, like some other literature? You might will say in the future that you're gonna define the gradient as the derivative of the transpose derivative. So if we define the gradient of the transpose derivative, there's at least one thing you feel comfortable. That is, if y is a scalar. Okay. If y is a scalar, remember we got dy equals a times dx, right? So y is a scalar, dx is a column vector, and a here must be a row vector, right? But if you define like dy over dx must be a transpose, so now your gradient becomes a column vector as well. So you might feel more comfortable at this case, right? However, when you apply the chain rule, you cannot do things like this. You can not compute partial y or partial x times partial x or partial z from left to right. You have to do it reversely. You have to multiply from right to left. Does it make sense? Okay. But in whichever case, that's fine. It's just about like how you feel comfortable to organize the elements in your gradient. But the key thing, right, which is invariant, is the derivative. As long as you can write down the derivative of y equals to something times x dx, you get your gradient, right? No matter if your gradient is defined as a or a transpose. Right? So the question in matrix vector derivative then becomes like, how do we derive? Remember, y can be a quite complicated form regarding x. Y can be vector, scalar, or even matrices, right? X can be vector, scalar matrices, right? When you derive dy equals to a times dx, like through a series of steps, then you can tell, okay, this is your gradient. Okay. And as to why you're going to use a or a transpose as a gradient, it doesn't matter. So far, so good. Any question? Anyone feels? Is there anyone feeling uncomfortable? I'm just make a little bit general definition about derivative and gradient. Okay. Just let me know if you feel anything uncomfortable. Okay. So as we just mentioned, in whichever case, right, in whichever definition of your gradient, the key is actually to derive or compute the derivative, right? How do you take the derivative of y, which can be written as a kind of linear transform of your derivative of input x. So when we manually derive the derivative of matrix or vector functions, the general strategy is to recursively apply the chain rule to get the target derivative. Namely, you're gonna use a bunch of calculation, merging, communication laws, all kind of stuff, like get the final form dy equals to a times dx. Right? That's the key idea of doing matrix vector derivative. But what kind of a chain rule can we use, right? So obviously, like all these scalar functions, those things we're familiar with, are not sufficient, right? So next we're gonna talk about how to apply the chain rule recursively to get those, right? But again, we're gonna start with a simple scalar case, which everyone feel easy and straightforward, right? For example, if I know y equals to 3x plus 1 over x squared, right? Now, if I want to derive dy equals to something times dx, how can we do that? Can anyone give me a hint? We just look at here, right? So when we calculate dy, that means we take a derivative over this guy, right? I know that this I think it's a fundamental rule is kind of like you react like instantly, right? From your instant, you're gonna decompose as d times 3 terms plus d times you decompose it as like d 3x plus d 1 over x squared, right? Because there's summation of two terms, so their derivative of summation is summation of the derivative, right? So d 3x plus d 1 over x squared, right? And for this guy, because it's a constant, multiply a variable, so we can just move the constant outside. So this guy is 3dx, right? And how about this guy? Yeah, take -1. Yeah. So we're gonna have to recall some rules we have used before. At least we were familiar before, right? So know that okay, this essentially is a dx minus 2 to the power of -2, right? So we know that there's some rule that if you take derivative of x to the power of a is constant, it is a times sorry, a times x a minus 1 dx, right? This is a rule. This is the basic rule, right? So we just apply here. It will give us -2 x minus 3 dx, right? So now I've got two derivatives, 3dx times this -2x minus x to the power of -3 dx. We just merge them together, right? So it's 3 minus 2 x minus 3 to the power of -3 dx, right? Which is dy. Does it make sense? Okay. And then we can get our gradient, right? dy over dx. This is just a simple scalar. Sorry. It is 3 minus 2x to the power of -3, right? This is how we practice our scalar function derivative, right? I hope no one feel confusing here. So now we need to extend our library of chain rule to matrices and vectors. So now we know that okay, in scalars, like we have like derivative of two terms like dx plus y equals to dx plus dy, right? And dx times y equals to dx times y plus x times dy. All those kind of basic laws, right? And what if we meet with matrices vectors? So first, those basic laws still apply to matrices vectors. Okay. So here, I just copied some reference. So they use partial symbol, but is actually the derivative symbol is same thing, right? So basically, if your matrix A is a constant, then its derivative is simple 0. Right? It's the same as the scalar case, right? And if you have a scalar constant, scalar alpha times your matrix variable x, then the derivative of alpha times x equals to alpha times derivative of x. So you can move the constant alpha outside, right? If you want to calculate derivative of summation of two vectors or two matrices, it is equal to calculating the derivative of each matrix or vector and then add them together. Right? And also, if you want to compute the derivative of the product between x, y, it is equal to partial x times y, derivative of x times y plus x times derivative of y. Okay? It's the same thing. Okay? But here, you should just be aware that x and y can be two matrices of different sizes. Right? This can be like matrix multiplication. X can be, say, m by n, and y could be n by q. Right? But this rule still applies. Right? Then the remaining thing are quite different. If you take a look, what is the derivative of trace of x? So how many of you have heard of trace operation? Okay, so what's the definition of trace? Yes, trace is the summation of the diagonal. So the trace must be applied to a square matrix. Right? So if you want to compute the derivative of a trace of a matrix, it is equal to first compute the derivative of x and take the trace. This is actually straightforward, right? Like you have a matrix, right? And you want to take the diagonal part, add them together. This is a trace, right? And take derivative. It is equal to, okay, first take the derivative of every matrix element and pull out the diagonal part, add them together. And then the remaining rules are very commonly used, but typically it's different from what I'm saying in the scalar world. Right? Like x circle y here, circle means like element-wise product. It's not matrix multiplication. It's element-wise product. That means x and y must have the same shape. Right? So if you do the element-wise product between two matrices, then the derivative equals to dx element-wise product with y plus x times element-wise product with dy. And this one is called a Kronecker product. How many of you have heard Kronecker product? Okay, great. So basically, Kronecker product, the definition is like this. Right? So if you want to compute a Kronecker product with B, right? So that basically means you're gonna create. Let me write is aij, right? So a that just indexes every element in A, right? So a Kronecker with B just means you're gonna times each single element of aij with B, and then form a block matrix. So like, for example, if you have just a 2x2 matrix, for A, right? If you want to connect it with B, it is just A11 times B, A12 B, and A21 B, and A22 B. Right? But now here, it's a block matrix, right? Because B is a matrix. You multiply this whole matrix with every element in A. So actually, you form a new block matrix. That's the definition of Kronecker product. But don't worry about that. We our topic won't relate too much about Kronecker product. Just to let you know, in the future you might have to deal with Kronecker product. But you see that there are many nice properties of Kronecker product. But anyway, the derivative of a Kronecker product between matrices they can be decomposed in the same way as you do M-wise product and also normal matrix product. So this is a very nice property, right? And derivative of X inverse. It won't be as easy as like derivative of 1 over X, which is minus X minus 2 dx. Won't be that easy, right? Because here now X is a matrix. And of course, we're gonna assume like x is invertible. So derivative of x inverse is defined this way. It's minus x inverse times dx times x inverse. It's a very well-known result. But you don't need to worry about how to prove that. We want to ask you how to prove that. I don't know how to prove it as well, but it's very famous rule summarized by some pioneer mathematicians. And what is the derivative of determinant of x? So another result, right? Determinant of x is derivative is determinant of x self times trace of x inverse times dx. And if you want to compute the log determinant of x and its derivative, it is trace x inverse dx. And actually, this rule can be derived directly from this. Right? I will leave it as an exercise for you. I just apply the chain rule, one-step chain rule and get it. And finally, I want to mention is that this is also very simple. Like derivative of transpose of x is transpose of the derivative. Right? So overall, these are a set of like most useful chain rules when you derive or calculating. We will derive and calculate the matrix vector derivatives. And once you have some kind of objective function, right? You want to derive the derivative with respect to some input vector or input matrices, right? You're gonna mechanically and recursively apply those rules to organize and get some kind of formula like dy equals a times dx, and then you get a derivative. That's how we manually derive those things. Right? So next, I'm gonna use two concrete examples to showcase how we're gonna apply those rules to get matrix vector derivatives. So the first one is a scalar function. So y is a scalar. Why can we say it's a scalar? Any thought? What? Yeah. This is the first observation. You have another observation? Yeah. Great. Yeah. So first, we keep a good notation custom. So from the from the shape and from its non-bold, we can say, okay, it's a scalar. Second, from the definition, we can see it's actually an inner product, right? A dot product between two vectors. So it must be scalar. So let us try to derive dy over dx. Right? Okay, to do that, we just want to derive dy. Right? So dy is equal to this guy, right? So that means dy equals to derivative of x plus b transpose x plus b, right? So now, if we look at the rule we just went over, right? We know that the derivative of two multiplication or product of two matrices, right, is equal to dx times y plus y times dx, right? So here is multiplication of two vectors, which you can still build them as like matrix, right? So so that means we can apply the rule we just I'm saying, so which is we first apply derivative over the term, the first term, and then times x plus b, right? And second, we keep the first term, which is x plus b transpose, and take the derivative of the second term, right? Does it make sense? And then if we want to take a derivative of transpose something from the rule, we have just seen, right? Derivative of transpose is a transpose of derivative, right? So that means we can first do the derivative and take transpose. So that is d x plus b transpose times x plus b. Right? Now let us look at the second one. Second one, the first term is still x plus b transpose. And second one, it is derivative of x plus a constant. Right? So know that derivative of x plus a constant is dx plus db, that the derivative of constant is simply 0. So dx plus b is simply dx. Right? And similarly, we have the result here. So it's dx transpose x plus b plus x plus b transpose dx. Right? So remember, we want to organize the form, the final form, to be something like this, right? A times dx, right? So it looks like our final form shouldn't include any dx transpose, right? We have to get rid of this, right? How can we do that? Because in our first term, we have dx transpose times x plus b, right? The second term is x plus b transpose dx. Right? So of course, we don't want dx transpose. How can we get rid of this or sidestep this? So we need to observe the shape of this, right? Remember, always when we're doing some matrix vector operations, always keep in mind what's the shape and what's the size of their result, our intermediate result, right? So what's this product? It's a vector, it's a matrix, all scalar. It's a scalar, right? So that means for any scalar, if you take a transpose, it is itself, right? Does it make sense? If you take transpose of 3, it's still 3, right? It won't be negative 3. Right? So similarly, if you take transpose of this scalar, it won't change. Right? So I can take transpose over there. That will give me x plus b transpose dx. Right? So now you get rid of dx transpose. Right? Right? And from another view, like dx transpose x plus b, you can visualize the dot product or inner product between dx and x plus b, right? So it doesn't matter, like you first transpose x plus b and then multiply with dx, or you first transpose dx, multiply with x plus b, right? The dot product is the same. So in this way, we know that the first term is actually x plus b transpose dx, right? And the second term has the same form. So now we just merge them together by multiply a factor 2, right? So now we have obtained the final form we want, right? So what is dy or dx now? Anyone can just read it? Yeah, that's it. That's our that's our final results, right? That is I'm sorry. That's our dy or dx, right? Of course, you can just use 2x plus b, right? To get rid of this transpose, that's following other definition, that's fine. But it doesn't change that the essence, right? Okay, this is the first case. Next, let us look at second case, right? This one. This one appears to be a little bit more challenging, right? But it's a good practice to apply all the new rules we have said. Right? So I'm gonna create a new page, and then write the function y trace I plus x transpose inverse Yeah, that's it, right? So again, our goal is that we want to derive the derivative as in the form of a times dx, right? Again, y here is the scalar. Y is a scalar. In addition to a reason that y is a non-bold, unbold, and Italian. Mhm.
We'll take the trace.
Yes, exactly. That's the definition of trees, right? Tree is the summation of the diagonal, so it must be a scalar. Right? But x here is a vector. Okay? So now let us try to derive dy, right? So dy equals to the trace of this matrix. Okay. Now just look at our dictionary. Okay, we know that here, right? The derivative of trace of something is equal to trace of derivative of that thing, right? So we're gonna just move derivative inside the trace, right? So this will give you trace of d I plus x transpose inverse, right? So if we denote this guy as let me denote as b, right? So you're actually computing derivative of the inverse of b, right? So now we have to deal with derivative of the inverse matrix. That's something we have just mentioned, right? Here, we found out the item in our dictionary. Derivative of x inverse is minus x inverse dx x inverse. Okay? So we're gonna apply this rule here. So it gives us it is equal to minus b inverse db and b inverse, right? And this minus sign is really annoying inside the trace operation. I'm gonna move it out, right? So it will give you trace and minus, right? So here, so remember, eventually, we're gonna want to our derivative to be on the rightmost side, right? So I don't want to stay in the middle. So, but dB is kind of like in between two B minus. It's B inverse. It's really awkward. So I'm gonna utilize some knowing property of the trace operation to rotate position. Okay? So what kind of trace operation property we're gonna use? This is a very well-known property. Like in general, right? If we're doing trace of the product of three matrices A, B, C, right? We're assuming that the matrix shapes are kind of match. You don't need to worry about if they can multiply or not. Right? This trace equals to, you can move C to the rightmost, right? C times A and B. You can move A to the rightmost. B, C, A. Right? It doesn't change the results. So that means you can just rotate the order of this matrix are like anti-clockwise. Like it doesn't change the result. It's a very well-known result. So now we're going to apply this rule in the trace operation, right? So we're going to move this B minus to the leftmost, right, inside the trace, so that my derivative of B will be on the rightmost, which makes me feel much more comfortable. So this will give me minus B minus B minus and dB. Okay. So now let us deal with B, right? B itself. So know that B is essentially this identity matrix times vector X and vector X transpose this guy, right? Again, we're gonna apply the chain rule, right? It is equal to derivative of I, which is constant, so it's 0, right? And then it's dx X transpose, right? And how do we derive dx X transpose? Right? Yes, 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 we have just used that product rule, right? So here again, right? The derivative of x times y equals to derivative of x times y plus x times the derivative of y, right? So again, use it. Right? So this guy, it further equals dx times x transpose plus x transpose, oh, sorry, plus x dx transpose, right? So now we got our derivative of b, right? We'll just substitute that back here. Does it make sense? Right? If you didn't catch up, that doesn't matter. Right? We can practice later. I just want to show you how we mechanically look up those dictionary and apply the rule here, and then arrange the terms to get a final form in this form, right? So if we substitute our d of b, which is in terms of d of x, into the trace, right? So we get minus trace. I'm gonna still use the same color, which is minus trace b minus b minus dx times x transpose plus x dx transpose. Right? So now let us just use a distributive law, right? We just multiply b minus into these two terms, right? So we got so we got this trace term b minus dx x transpose, right? Minus trace term b minus x times dx transpose, right? I just multiply this b minus to each of these term in the parentheses, right? And then apply the trace operation, because trace of operation of a plus b equals to trace a plus trace b, so it doesn't matter, right? And we have negative sign outside, so I just put negative sign in each of them. Does it make sense? Right? So multiply this guy. Multiply this guy to here and also to here, right? So you got a trace. So that means you got a trace a1 plus a2, right? And then this is equal to trace a1 plus trace a2. Does it make sense? Right? And you have minus sign in front of it, so you must have minus sign. It's really bad writing, right? So it's trace a1 plus trace a2 equals to trace a1 plus trace a2, right? And you got a minus sign in front of it, so you got front minus sign here, you got minus sign here, right? That's how we got this, right? So now let us look at these two terms like one by one, right? The first term, sorry. The first term, this dx, again, is in the middle, right? Which is kind of annoying. I'm gonna use this rotation property of trace operation again, right? I'm gonna move x transpose to the leftmost. So it immediately gave me minus trace x transpose b inverse e of x, right? That's the first term, right? So now, again, as we said, right? Always keep in mind what's the size, what's the shape of your result. What's the shape of this? Any thought? Think about it. Yeah, inside the trees. Yeah, it could be a square matrix, but in this case, what is it? What's that? You mean this is like suppose X is n dimensional, this one is n by n? Okay, let's look into it, right? Okay. So dx is n by 1 vector, right? So X transpose is 1 by n vector, right? And B minus, right? B, the definition of B is here, right? So B is a n by n matrix for sure. So now, can we see what's the size of X transpose B minus dx? It's a scalar, right? It's just scalar, right? So if we're doing trees of scalar, that means it's scalar itself, right? Because the scalar has only one diagonal element, that is itself, right? So you can just get rid of trees, right? Don't forget we are minus sign here, right? So now let us look at the second term. So for the second term, we're going to leverage another property of trees operation. That is trees A equals to trees A transpose. Why? Why is this true? Yes, exactly right. This A matrix, this square matrix, is not necessary to be symmetric, right? However, if you do the transpose, it doesn't change the diagonal. You might change the lower triangular part and the upper triangular part, right? It doesn't change the diagonal part. So if you look at this one, the inside term, the inside result is the result inside the trace, right? So what's it? It's a scalar or it's a matrix? It's a matrix, right? So just keep forcing you to think about the matrix shape every step, right? So why? Because it's B is n by n, right? And B minus n by n. X is n by 1, while dx transpose will be 1 by n, right? So this guy, when they multiply together, they will end up with an n by n matrix, right? So now we're gonna apply this rule, right? If I take the transpose of this matrix, I won't affect the trace result, right? If I take the transpose of this guy, what can we get? What's the transpose of this B minus X dx transpose? Let us apply the rule of doing transpose over the product of the matrices, okay? So we're gonna doing the transpose of every term in the product and then reverse order, right? That's what we have learned from linear algebra, okay? So that means I'm gonna do the dx transpose and transpose again and put it in the first term, right? Which is dx, right? Let me use another color. Which will be dx, right? And then second term will be x, now it becomes x transpose. And third one is B minus, right? B minus transpose. And third one is B minus transpose, right? And then we take the trace. The result is the same, right? So if you look at B here, what is B transpose? B is identity plus X transpose. So that means B is symmetric, right? B is symmetric. So, so B inverse transpose, this is the basic rule of matrix, right? Is B transpose inverse, which is B inverse, right? Because B itself is symmetric. So now, after doing transpose of the term inside of the trace, we got it is dx times X transpose B inverse B inverse. Okay. So now we're going to use the rotation property again. Remember, we can rotate the leftmost term to the rightmost term inside the product, inside the trace, right? So we can move dx to the rightmost, right? So give me dx here. So now what can we observe? It's same as the first term, right? So we can get rid of trace. Remember, there's the minus here. So actually, this term and this term the same. So we can just use multiply a factor of 2, right? So now we got our derivative, right? This is dy. dy to this, right? So what's the derivative now? Or what is the gradient? Just this guy, right? That's how we get a result. Okay, so this practice example is a little bit kind of lengthy, but it's a good example to show, okay, how you kind of like leverage different rules in your matrix vector library and chain rule, and also the size of the intermediate results or the shape of intermediate results to organize your results and give you the final form. And hopefully, if you feel the last problem, or forgot our second last problem, yeah, homework 0 is difficult, then you can think about this example. And if you can follow this example, then those problems are really much simpler than this. Any questions so far? Okay, I highly recommend you, like after the class, you just follow what I have practiced in the class and to do this again, right? That will definitely deepen your understanding about how you're going to do like matrix vector derivatives, those kind of stuff, right? Okay, so although we just list the set of like commonly used rules, very, very popular, very, very useful. But if we want a more complementary dictionary, right? We suggest like 2 references, right? One is written by Tom Minka in 2001. It's called Old and New Matrix Algebra Useful for Statistics. You see a lot of rules summarized by Minka. Another one is even more popular. It's called Matrix Cookbook. It's summarized by researchers in University of Toronto, and it's released and spread it in the internet for at least 10 years. At least when I was a PhD student, that book has already been quite popular. So I guess that won't be at least 10 years. Yeah. And usually, if you want to derive matrix or vector derivatives, what you do is that follow the general procedure as we just showcased, right? Just look up those dictionary or reference books and look up the rules and apply your intermediate results and organize them and look at the size and shape of intermediate results. You might take transpose. You might apply the trace operation rules and all kind of stuff to merge the results, and finally you end up with some formula like dy equals a times dx, then you're done. Okay. Okay, next we're gonna introduce the definition of a convex function. Right? This is also very, very important for probabilistic learning, because the K technique in probabilistic learning, one of K technique in probabilistic learning is called a variational inference. It essentially build upon the property of convex functions called the Jensen's inequality and also the convex duality, right? So convex function is defined, domain of convex function is defined on a convex regional set. So please bear with my a little bit cough. So what is a convex region or convex domain? It means that if 2 points are both inside this domain, and if you draw a segment or draw a line to connect x and y, you need to be sure that every point on this line, which connecting x and y, and in between must be inside this region as well. This is called convex. So basically, can imagine this region must be kind of outward. It doesn't have any inward part. For example, for this one, for this region, it's not convex region. It looks like conic, but it's not convex. Why? Because if you pick out x and y here, if you draw a line in between, right, and this red part do not belong to the region, so it's not convex. Does it make sense? So what is convex function? Many of you have heard of it before, so I just repeat, right? Convex function is defined on convex region or convex domain. It requires that, okay, for arbitrary inputs, two inputs x1, x2 in your domain, and pick up arbitrary ratio t between 0 and 1. Then if you evaluate the convex combination of x1 and x2 according to t, basically means at tx1 plus 1 minus t times x2, the function value at this combination of x1 and x2 is less than or equal to, you first evaluate the function at x1, x2, and then do this combination with t. So basically, the function value of the combination is less than or equal to the combination of function values. So this the text description of this rule is kind of lengthy, but if you use a graph to explain, it's much more intuitive, right? So this is a typical convex function, right? If you pick up x1, x2 arbitrarily, which is your x domain, right? So then we can see that for any convex combination of x2 and x2, right? So that means any point in between x1, x2. This is where the function value at the combination of x1 and x2, right? And this is where the combination of function values at x1 and x2. Okay. So you can see that the latter is above the former, right? So that's typically how it satisfies the definition, right? So actually, you can pick up arbitrary 2 points and pick up arbitrary points in between, right? Like here, this is where the function value of the tx1 plus 1 minus tx2, right? But if you combine the function values at x1, x2 is here, right? So it's still below. Any question regarding definition? I assume everyone feels like straightforward about this, right? Okay. So here are some examples of convex functions, like, for example, if a single variable, then exponential function or negative logarithm are all examples of convex functions, right? If you have a vector function, meaning that your input is vector, then linear function is a convex function, and quadratic function is convex function. So how do we check if a given function is convex or not? If this function itself is differentiable, then we have for any xy in your domain, this inequality is satisfied, then f is a convex function. So let us see what does this mean, right? So that means for arbitrary x, right, you get fx is no less than f of y plus the gradient of f of y in the product with x minus 1. So what does the right hand side mean? What does right hand side mean? Any thought? It's a tangent line, right? Remember, this guy is actually the slope, right? Like if you if you draw a convex function, right? So if this is your y, right? If you want to draw a tangent line, right, at y, and use another, right? Okay. So the form of this tangent line is f of y plus gradient of f at y transpose x minus y. So this is your tangent line. Let me denote it by g of x. Okay, this is just the extension of the scalar case, right? We know that if the scalar function, like if you want to write the tangent lines, it just replaces this by a 5y, okay? The same thing. So what does this result tell us? This result tells us that for arbitrary x, your function value is no less than the value at the tangent line. In other words, the whole convex function body is above any of its tangent line. That's a very nice property, right? So you can try to draw other tangent lines, right? You can draw here, you can draw here, you can draw here, right? You see that for every tangent line, it stays below the entire convex function body. Any question about this geometric meaning of this inequality? Okay. And the second common use probably is called Hessian or second order derivative. If f is second order differentiable, and if and any input x is Hessian matrix is a semi-positive definite, then f will be convex as well. We're not going to prove why this is the case, right? But this is a knowing result in the convex functions properties, right? But just keep in mind, this is very often used property. Okay, let's stop here today. So Thursday we're gonna continue with the Jensen's inequality and also convex duality.